Hello everyone, my name is Carly Bast and I am a graduate structural engineer at Buro Happold in New York City. Thank you for attending this presentation. I'm pleased to present to you my paper, New Shells, New Drivers, which I completed with my colleagues Michael Hoehn, Cristobal, Correa, and Craig Schwitter. In this presentation, I will introduce the topic, review 5 precedent projects, report our findings from the embodied carbon studies of each of these 5 projects, and discuss future recommendations for grid shell designers. Here we'll start with what are the current drivers of grid shell design? We often think of boundary conditions, these are the extents of the grid shell, but also in the context of this paper will include factors like architectural purpose, site restrictions, and city zoning codes. The next driver is the grid shell shape. How is the shape developed? Lastly, we'll look at the fabrication techniques. How will this grid shell be constructed, and what are the nodal and cladding strategies? In this paper, we'll identify these current drivers of 5 past projects to understand how these drivers are relevant. Lastly, a key discussion around big projects now is embodied carbon. What is the impact of the building on the environment? In this paper, we will run an embodied carbon analysis on each of the 5 past projects and identify key patterns. Lastly, we'll propose methods to improve our embodied carbon footprint and grid shell design. Next, we'll look at the 5 past projects. We start in 1974 with the Mannheim Multihall, followed by the Museum of Hamburg, then the British Museum, then the Smithsonian, and then the Jewel Changi. While we will be comparing these 5 projects, it is important to note that they are not of all the same size, the largest being the Jewel Changi and the smallest being the Museum of Hamburg here on the right. Starting with the Mannheim Multihall. As you may know, the Mannheim Multihall is a timber grid shell in Mannheim, Germany, intended to be a temporary outdoor structure, but it still stands today. The main driver for the shell was its construction. The timber lattice was formed flat, then raised up into its final position. This was possible due to the identical members and nodes. The nodes were loose when the grid shell was laid flat and then tightened when the grid shell reached its final form. It's also cladded in this PVC flexible cladding. Next, we have the Museum of Hamburg. The Museum of Hamburg is a steel grid shell in Hamburg, Germany, its form being defined by the existing courtyard extents, allowing for 2 barrel vaults to meet at a dome. A key driver was the ease and speed of construction. Most members and nodes are the same, but since there is no double curvature in the barrel vaults, the use of a bulkhead allowed for the members to be of the same section. Next, we have the British Museum. The British Museum is a steel grid shell in London, bound by the extents of the existing building. The boundaries include a rectangle with a circle offset from the center. The shape is a free-form geometry governed by visual lightness and minimal allowable forces on the existing building. The key drivers for the British Museum include minimal loads allowed on the existing building and discretizing for the free-form shape. Double curvature in the shape was used to achieve as much stiffness as possible, but there still is bending in the structure which requires large member depths. Since bending only occurs in certain areas, the member depths are tapered, which increases the complexity of the nodes. The nodes were created with CNC milling, which was at the forefront of steel fabrication at the time. Next, we have the Smithsonian. The Smithsonian is a steel grid shell in Washington, D.C. in the U.S. This grid shell is bound by the rectangular courtyard perimeter. On the inside of the perimeter are 8 existing foundations that support the grid shell, and no imposed loads are to be on the existing building. The key challenge for the Smithsonian include the height limitations on the shell shape. This restriction allowed for some double curvature, but there is still some bending in the steel members. This is addressed by deeper sections that are also tapered similar to the British Museum. Additionally, due to the rectangular grid, the planarity of the panels was achieved by offsetting the 4th corner, creating a scale-like effect. Lastly, we're going to look at the Jewel Changi. The Jewel Changi is a steel grid shell in Singapore. The free-form grid shell has no significant site restrictions, but has many architectural demands such as the large indoor waterfall, a train, and indoor plants. The key challenges for the Jewel Changi include the intense spatial requirements, which affect the grid shell shape, and the large scale. The large scale of the building created significant amounts of data, which require computational power to develop and understand. The nodal strategies were heavily influenced by the British Museum and Smithsonian. Now, we can look at the embodied carbon of each of the projects. We'll define embodied carbon first. We calculate the embodied carbon of a building through the first few phases of the life cycle assessment. We use the material quantities from our building and multiply them by our global warming potential to get our whole building global warming potential. Our workflow at Buro Happold includes our own BOMLA Toolkit created by our computational staff. This toolkit is open source and available free for the public. Specifically for grid shells, we're interested in the three main material categories: nodes, structural elements, and cladding. Here are the results from our embodied carbon studies for the 5 projects. Here we see the diameter of the pie charts indicating the total GWP per plan area. Mannheim on the left, we see the surface cladding take the majority of the GWP. This is because the structural members are timber, which are low embodied carbon, and the surface cladding is PVC, which is relatively high embodied carbon. Next, we have Museum of Hamburg, which is governed by the solid steel members. Next, with the British Museum, we see the nodes taking a more significant portion. This is due to the CNC milled nodes. With the Smithsonian, we have deep members taking the majority of the GWP. And last, with the Changi, the overall biggest structure with the highest GWP per plan area. But why is this? Why is our embodied carbon per plan area going steadily upwards, and how do we fix it? Now we'll look at our future recommendations for how we fix this. What we see with each project is there is more spatial demand on the space. We start with Mannheim, a temporary outdoor structure, and then going up to the Changi with indoor lighting requirements, air quality requirements, and not to mention the waterfall in the middle. These demands do come at a cost, and that would be embodied carbon. So as designers, how do we balance client needs with environmental impact? We need to start these conversations and expectations with the client early on. While we have been able to solve issues like planarity and node constructability, we need to start with the embodied carbon as our new driver. Thank you for listening to my presentation today, and I'll see you guys with the Q&A.